The universe around us, space on the one hand, amazes the imagination, for example, with its vastness, infinity, and incomprehensibility. It awakens the dormant explorer in each of us. On the other hand, none of us has, nor is expected to have in the distant future, the tools for this. I'm not talking about home telescopes, but something real, like huge radio telescopes.
Spacecraft.
None of us have or can have satellites or anything like that. That's why we have to completely trust a small group of scientists and astronomers and
Physicists entirely.
who have completely taken over this niche. But they are all people, and people tend to, how should I put it gently,
Make mistakes to be mistaken.
and persist in
Your mistakes blocking the way.
other ideas. Hello, this is Epocha Nedovaria, and today we will try to tackle one of the fundamental questions that makes all the folds in your brain twist into a Gordian knot, namely the expansion of the universe. It might seem, so what? Why should we care about the expansion of the universe in general and the Big Bang in particular? We seem to be dealing with history, trying to expose its forgeries, and such large-scale questions don't seem to concern us. I disagree. First of all, strangely enough, this concerns us directly, although in the most unexpected way. But I'll talk about that in future videos. Secondly, it's simply intriguing. Well, as usual, let's start in order with the classic interpretation of the question, and then we'll see where it leads us. So, the question about the universe we live in has concerned people almost since the dawn of civilization, and maybe even earlier. As soon as humans became self-aware, we became interested in knowing our place in the world. At first, we explored the world using our own senses: eyes to see, legs to move through space, hands to feel that very space and the amazing objects we encountered along the way. In general, that's how we made our way to telescopes, discovered the planets of the solar system, and looked even further. We became interested in how our universe is structured. And to understand that, we needed to grasp the fundamental laws by which it exists. And so, in 1870, the English mathematician William Kingdon Clifford, who was only 25 years old, came to the idea that space could be curved and not uniformly in different places, and that its curvature could change over time. By the way, the figure of this scientist himself raises a lot of questions. Well, just think about it. At the age of 23, he graduated from Trinity College at Cambridge University. By Soviet standards, that's just a vocational school level. However, he did graduate with honors. And just 3 years later, at the age of 26, he was noticed by Maxwell and, on his recommendation, immediately became a professor of mathematics and mechanics at University College London. However, he formulated his idea about the curvature of space a year before that, which means just 2 years after graduating from college. And 7 years later, he suddenly and unexpectedly died of tuberculosis, thus living only 33 years. In addition to the hypothesis about the curvature of space, in such a short time he managed to found an entire branch of mathematics, Clifford algebra, and was also one of the founders of vector analysis, and many other interesting things too. And just a year before his strange death, he put forward the idea that matter and gravity are manifestations of the curvature of space-time, an idea that would later be used by everyone, including Albert or Einstein. And all of this in just 10 years of his short life. And if such a person really existed, then he can rightfully be considered one of the greatest geniuses of the last 200 years. However, I bet that very few people have even heard of him. It feels like he was deliberately forgotten and silenced. The name William Kingdon Clifford is almost unknown to the general public. Let's note this to ourselves and move on. 15 years later, in 1886, the English astronomer William Huggins noticed that the wavelengths in the stellar spectrum were slightly shifted compared to the terrestrial spectra of the same elements. By applying the Doppler effect formula to this shift, the scientists obtained information about the actual speed and direction of the star's movement. And 35 years later, Edwin Hubble empirically discovered an approximate proportionality between redshifts and galactic distances, which he, using the Doppler-Fizeau formula, turned into a proportionality between velocities and distances. As you can see, astronomer scientists are not at all shy about putting forward empirical, that is, speculative assumptions, and creating very approximate patterns based on them. However, such things are allowed only for a select few. Nevertheless, mathematically, the universe was still considered static and finite. Even Albert R. Einstein thought so. In 1917, he came to the conclusion that our universe is a four-dimensional sphere. In our three-dimensional world, it has no visual representation, just like a four-dimensional cube, a tesseract. However, this principle of the four-dimensional sphere made it possible to calculate the mass of the universe, its size, and the amount of matter in it. The Einstein model allows you to move infinitely in any direction and eventually return to your starting point, just like on any sphere. That is, despite the finite amount of matter, the universe is still boundless. However, as it turned out, with the slightest deviation of the universe's radius from its equilibrium value, his model either begins to expand uncontrollably or also collapses uncontrollably. That is, it contracts. Simply put, the universe should have a center of gravity, preferably located at a single point in the center of the sphere. At this point, mathematics starts to turn from an exact research tool into, once again, a tool, but one that creates a construction convenient or necessary for the client. As the saying goes, the deeper into the forest, the thicker the partisans. Judge for yourself what they devised. For example, heavy nothingness. How does that sound, huh? Or virtual particle pairs that emerge from nothing near black holes, one of which evaporates, causing the synchronous evaporation of the other, which is, for example, inside the black hole. There are such formulations, patches, and paradoxical crutches in astronomy and physics at every turn. Yes, no, of course. Coming up with a heavy nothing is quite an achievement. However, when it comes to fundamental questions, they are unable to answer the question of why. They try, of course. They come up with Big Bang theories, a hot yet flat universe, and even Schrödinger's cats in the end. Here's another example for you. The notorious gravitational constant. Every day, we feel the effects of the force of gravity. The formula for calculating the gravitational constant for any object was derived long ago. However, somehow the notorious multiplier crept into this calculation, a fixed number without which the formula doesn't work. They added the multiplier and the formula started working. Well, that's the answer to the question of what, but not to the question of why. Where did this number come from? Why does it have this particular value? 6.67 times 10 to the power of minus 11. Nevertheless, the formula works successfully, and that's fine. This is an example of fitting. In fact, there are countless such fittings, but let's compare this factor with another equally notorious number. Here, everything is clear. The number is constant because it's simply the ratio of the radius of a circle to its circumference. In our decimal system, this parameter will always be 3.14.14. Yes, in fact, in any other system, it will remain exactly the same. Only the digits after the decimal point will change, but that will be related only to the base of the numeral system. That is, it's just the proportional ratio of the radius or diameter of a circle to its circumference. That's all. But here's what the factor in the formula for the gravitational constant represents. Well, somehow they forgot to explain it. Let me emphasize again, it's not about how it's calculated, but what exactly it represents. In other words, why is it exactly that value? What specific physical object or its form makes the value of the factor exactly what it is? However, almost every formula has an initial assumption that is not justified in any way, and all further reasoning and calculations are based on it. That's understandable. Our science is applied, and when the goal is achieved, when practical calculation and application are reached, then further research generally becomes unnecessary for anyone. And that's why it's unclear why Einstein's formula of a finite universe wasn't satisfactory. Why not accept it? A clearly fixed and balanced center. Well, it's just like with a number. No one would ever think about what would happen if a number shifted its value and suddenly became equal to 4. In our universe, that's simply impossible. Well then, let a static universe calmly exist as a four-dimensional sphere, and it would have a center of mass that can't be moved. Who would that bother? However, no, it's just like with electricity. Someone unknown made every possible effort to prove it. Specifically, the infinitely expanding universe with acceleration. Many other scientists also tried to build a model of the universe. De Sitter, Slipher, Poincaré, Lemaitre, Friedman, and so on. As a result, after Lemaitre identified the cosmological constant with the vacuum energy density in 1933, his model of the expanding universe was recognized by the whole world. Now let's figure out what exactly is this cosmological constant. And this is essentially the vacuum. Nothing that is almost zero. No, of course, there is a formula to calculate it, but it is so small that in reality, it is always neglected. The density of such a substance is less than 10 to the minus 29th power grams per cubic centimeter. This means that such a substance, even according to the scientists themselves, has no significance at all. Even on the scale of a galaxy, or even on the scale of a galaxy cluster, but it contains plenty of energy. You have to appreciate the beauty of the manipulation. All it took was finding the right correspondence, and everything worked. It doesn't matter what it looks like. Well, yeah, vacuum, that is nothing, has density, weight, and energy greater than 0. Yeah, vacuum, meaning nothing, is actually pretty heavy. So what? Will anyone ever explain it? Probably. For now, don't ask us questions. We don't understand it either, but at least it all adds up. And again, just like with the question about electricity, someone stubbornly and persistently, with all their might, tries not to step on the rake. In other words, refuses to acknowledge the materiality and existence of the ether. Although in one form or another, under the weight of various caveats and crutches, through the veil of physicists' psychedelic fantasies, the ether still peeks out here and there under different names. Sometimes the vacuum has density, sometimes the vacuum has weight and energy. In other words, it exhibits physical properties inherent to matter. But all right, what does that have to do with us? But we're meant to discuss the universe's expansion. Stay with me a bit more. So the main evidence for the expansion of the universe is the Doppler effect. That is, the stretching of the wavelength. So let's pay a little more attention to it so that every viewer understands exactly what it is. Light is one type of electromagnetic radiation, a wave that has a certain range of frequencies. Depending on the wavelength in the visible range, we perceive colors. The higher the frequency and the shorter the wavelength, the more it shifts toward blue and even violet. The longer the wavelength, the more it shifts toward red. Green is roughly in the middle. So, if an object emitting, for example, green light, with a frequency, with a wavelength amplitude of, say, 1, moves toward us, the light wave becomes shorter. Well, simply because each subsequent crest of the wave is emitted a little closer to us each time, which means the wave itself becomes shorter and more intense, and its value decreases from 1, for example, to 0.9. In this way, It shifts first into the blue, then into the violet parts of the spectrum, and so on, depending on the speed of the object. But if the object is moving away from us, then everything happens exactly the opposite. The wavelength increases, for example, to a value of 1.1 or even more, and it becomes redder and redder. Speed detectors on the road work in exactly the same way. Thanks to the change in wavelength, they determine not only the direction, but also the speed. You break the rules and then you get a well-deserved fine. I hope this example is clear to all. So, back in the century before last, it turned out that the vast majority of galaxies are redder than they should be, and only 4 out of the 40 known at that time were bluish. It turns out that all galaxies are moving away from us, but what's most surprising is that they're doing so at almost the same speed. More precisely, at equal distances from us, the galaxies are receding at roughly the same speed. How is that possible? And so, a seemingly logical conclusion suggested itself. The universe is expanding. Moreover, it's not just expanding, but doing so at an ever-increasing speed. This is indicated by the difference in redshift. The farther a galaxy is from us, the higher its redshift, and the faster it is moving away. It is quite possible that this very fact prompted the desire to mathematically explain the expansion of the universe. However, before Lemaitre, almost all calculations indicated that the universe was static. In general, Lemaitre found a way to force everything to fit, and the scientific community calmed down a bit.
You can't rely on anyone. You have to do everything yourself.
Although to do this, he had to introduce the formula of heavy nothingness, which possesses a colossal amount of energy. Moreover, this very nothingness, or ether, matter was divided into 2 conditionally independent parts: dark matter and dark energy. It is strongly not recommended to confuse them. And all of this together, unseen energy and unseen matter, make up as much as 96% of the entire composition of the universe. Well, that is almost everything. But why were they separated? And that's the most interesting part. The thing is, both dark matter and dark energy are needed in the equations to explain the missing gravitational interaction between galaxies. Dark matter can be unevenly distributed, with varying amounts in different locations, and may not exist in some places at all. And in this way, it is used to explain gravitational anomalies. But dark energy is considered pure gravity, without being tied to any material object. And it supposedly fills all of space evenly. To make it easier to imagine, picture a swimming pool filled with water, with large and small ice cubes floating in it. Both are water, but the liquid water fills the pool evenly. And in our case, that's dark energy. But the ice cubes are denser and heavier pieces, floating around randomly. They're also water, but much denser and more tangible. That's what's considered dark matter. Now let's pause for a moment and think. Is the expansion of the universe really the only possible explanation for all galaxies shifting toward the red spectrum? Are they really moving away from us at tremendous speed? No, it's not the only one. But to understand how this works, let's recall another interesting physical effect. It's called gravitational lensing. It consists in the fact that when light passes near a massive gravitational object, it slightly changes its direction and wavelength. This is exactly how, for example, black holes are found in the universe. It's impossible to see a black hole itself. No one, not even light that crosses the event horizon of a black hole, can escape back. However, if light from a star passes close to the event horizon, its direction changes and it sort of bends around, bypassing the hole. By observing this process, we see how the star seems to jump from one place to another, gradually returning to its original position over time. This optical effect is called gravitational lensing. It's as if a lens passes between us and the star. By the way, since we called this effect lensing, it means that light undergoes similar transformations not only near black holes. The very word lensing directly tells us that this effect can also be observed with an ordinary lens. We'll develop this interesting idea some other time. But now let's focus specifically on the gravitational effect. It manifests itself near any object that has gravity, for example, near ordinary stars. Of course, to a much lesser extent, but this effect does exist. And thanks to it, we also discover other exoplanets. I already mentioned this method in the previous video. But that's not all. After all, essentially any cosmic object, whether it's a galaxy, a black hole, a star, or a planet, all of them have gravity. Some have more, some have less, but nevertheless, all of them have it. Moreover, theoretically, a gravitational field has no boundaries. According to the most common version of visualizing this process, a massive object sort of presses down on space with its mass, creating a kind of spatial funnel that we continuously fall into and call this the force of gravity. And now let's put together everything we've just learned. First, the light from a star is a wave of a certain frequency. Second, all objects in the universe have at least some gravitational field. Third, we are in the gravitational field of the Earth, which in turn is firmly embedded in the gravitational field of the Sun. Conclusion, all of us, all the planets of the solar system, are inside the Sun's gravitational lens, the tangible boundary of which is far beyond the Oort cloud, that is, farther than 50,000 astronomical units. And throughout this entire distance, the Sun's gravity is at work, pressing down on space and stretching it just a little bit. The light from stars, before we see it, inevitably passes through this gravitational lens, this funnel, a place with stretched space, which in turn naturally stretches the light wave itself, thus lengthening it and shifting it into the red spectrum. In other words, with this logic, we will inevitably see the spectrum of any object shift toward red, and it will always seem to us that objects are moving away, even though that's not actually the case. The acceleration will be about the same at equal distances, and it will increase as the object moves farther away. And since the gravitational field is practically infinite, as the distance to the object increases, the wave will stretch more and more, which will also inevitably create the illusion of the acceleration of the expansion of the universe. Let's take our reasoning even further and assume that there are entire regions of heavy, compressed space along the path of light from distant galaxies. Especially since modern astronomy doesn't really deny this. What will happen to the light next? And then, the wavelength will keep stretching more and more until it leaves the visible range and enters the radio wave range. So, at a certain distance from us, the distortion of the wave in the gravitational well will become so strong that light will turn into a radio wave. And what will happen even farther away? According to the official theory, scientists talk about the event horizon, when the recession of galaxies reaches the speed of light and we stop seeing them. Well, yes, it seems logical, but what will it look like? According to our theory, the wavelength will keep getting longer until it goes beyond the observable range. As the light wave gets longer and shifts into the radio range, another effect will occur. We will stop seeing them. By the way, this is an alternative explanation for why space is black. But in the radio range, we observe the entire cosmic microwave background radiation from all directions. Space literally glows with it. Some people claim that it appeared right after the Big Bang. However, if we keep straightening the waves at some distance Just before everything turns completely black, we actually get an image of the background cosmic microwave radiation. Well, we've figured out the Doppler effect, but what about the instability of a static universe? Remember, as soon as the mathematical model deviated from the equilibrium value, it immediately collapsed either into expansion or contraction. Actually, everything here is also very simple. Imagine a vessel completely filled with liquid. The pressure of the liquid inside the vessel distributes the load evenly in all directions. And if there is some object floating inside such a vessel, for example, a fish, then regardless of its position inside the vessel, it will never lose its equilibrium value. Its center of gravity will never shift, precisely because the water distributes the load evenly throughout the entire vessel. For this to work, you need just a little: the existence of ether and the pressing of matter by gravity. However, despite everything, instead of ether, the concept of heavy nothing was introduced. And also, lately, incredible efforts have been made to move away from a popular, simple, and understandable example, with the squeezing of space. By the way, remember where we started? Our genius from the century before last, who passed away too soon? William Kingdon Clifford. Let me remind you that he was noticed by Maxwell and made a professor almost immediately after he suggested that space itself could have inhomogeneity and curvature. Of course, these are just my assumptions, hypotheses, my personal alternative view, but somehow everything seems suspiciously twisted around the existence of the ether. Don't you think so? Friends, none of us are immune to mistakes. And if you spot a flaw in my logic, don't hesitate. Leave an angry comment under the video, clearly and confidently.